Artificial intelligence, or AI. It is a very exciting field. It is all about building smart machines. We want these machines to perform tasks that usually require human intelligence. For a long time, programmers tried to do this by writing very specific rules. Imagine trying to write rules to describe a cat. Pointy ears, whiskers, fur. But some cats have floppy ears, and some dogs have pointy ears. Writing rules that cover every single possibility is extremely difficult. This is where a different approach becomes useful. Let the machine learn on its own. We do this by showing it many examples. This is called machine learning. Like a child, we do not give rules. We point at many dogs and say dog. The brain learns patterns. AI learns similarly from vast data, pictures, text, sounds, discovering patterns and getting more accurate. So, what exactly is a neural network? At its core, it is a computer program designed to mimic the human brain. Our brains have billions of interconnected neurons that receive, process, and pass signals. A computer neural network copies this basic structure. It is not a physical brain. It is virtual, built with code. It is made of simple processing units called neurons or nodes. Each does a tiny calculation. A neuron receives one or more inputs, computes, then produces an output signal. Power emerges when many units connect together. The whole becomes greater than the sum of its parts. Like a company, one expert in marketing, another in finance, another in design. No one runs it alone, but together they launch a product. A neural network works the same way. Each neuron does a tiny task. Together they can, for example, recognize your face. Learning means adjusting connection strengths, called weights. Stronger weights influence more. Training finds the right set of weights, tuning again and again to focus on important signals and ignore noise. To keep things organized, neurons are arranged in layers. Imagine layers as departments with specific roles. A simple network has three types: input, hidden, and output layers. Information flows in one direction, from first to last. This structure transforms raw data into useful answers. The input layer receives raw data, like a mailroom receiving packages. For images, inputs are pixel values, brightness and color. For text, inputs are numbers representing words. The input layer does not compute, it passes data onward. Hidden layers sit between input and output. This is where the real magic happens. A simple network may have one hidden layer, complex ones have many, each detecting increasingly complex features. Finally, the output layer produces the prediction, like a CEO delivering the decision. Outputs depend on the task. 2 neurons for cat versus dog, or 1 neuron for a price. Now that we understand layers, let us follow a piece of data through the network, the forward pass. We feed an image to the network. It is a grid of pixels mapped into the input layer. Each input neuron takes one piece, say a pixel brightness, and passes it on. In the hidden layer, a neuron multiplies each input by its weight and sums them. High weights matter more, low weights matter less. Then, an activation function, like a dimmer or gate, decides if the signal passes and how strongly. This non-linearity enables learning complex relationships. The process repeats layer by layer. Early layers detect simple edges and colors. Later ones combine them into shapes, ears, eyes, a tail. The output layer computes the final prediction. For example, 95% cat and 5% dog, the network's best guess. A neural network is not very useful at first. Its weights start as small, random numbers. Initial predictions are wrong, like a student guessing on the first test. The most important part is training, learning from mistakes to get smarter. We need many examples with known answers. Take an example, run a forward pass, get a prediction, compare to the correct label. The difference is the error or loss. Big loss means a big mistake. We then use backpropagation, working backward from output to input, to compute how each weight contributed to the error. We decrease weights that led us wrong and increase ones that would have helped. Like a coach giving targeted feedback after a bad play. Forward pass, error calculation, backpropagation, repeated thousands or millions of times across the dataset, nudging weights in the right direction. Over time, predictions become accurate. The network learns internal rules, encoded in weights, to generalize to new images. This is learning in a neural network. Going deeper. What is deep learning? You may have heard deep learning alongside AI and neural networks. Deep learning equals neural networks with many hidden layers. Deep refers to number of layers. 1 or 2 is shallow. Tens, hundreds, even thousands is deep. More depth means greater capacity to learn. Think Lego. A single layer makes flat shapes. Add layers to build complex 3D structures. In images, early layers detect simple spots and edges. Deeper layers combine them into shapes, textures, parts, like eyes or wheels, and finally, full objects. This layered learning is powerful and automatic, but it needs large datasets and strong compute, often GPUs. Despite the cost, deep learning is state-of-the-art for many hard AI problems. Neural networks and deep learning are everywhere, powering services we use daily. Learning from data unlocks capabilities that feel like magic. Image recognition. Social apps suggest tags, trained on millions of faces. Healthcare. Models help analyze scans to spot disease earlier and more accurately. Natural language. Voice assistants transcribe speech, understand intent, and respond, powered by massive language models. Self-driving, cameras and sensors stream data, networks detect cars, pedestrians, traffic lights and lanes, then predict motion to decide when to accelerate, brake, or turn. Near human perception, enabled by deep learning. Recommendations? Systems learn from your watch, like, and purchase history, comparing across millions of users to find what you will love. The result? Surprisingly accurate, personalized suggestions. From your camera to hospitals to cars and storefronts, neural networks power modern AI. Sometimes simple analogies help most. Think of layers as filters. First, is it red? Then, is it small and heart-shaped? You narrow to strawberries. Similarly, early layers detect simple cues. Deeper ones detect complex combinations. Stacking filters enables recognition and clutter. Training is like darts. You miss, measure the error, adjust your aim for next time. Backprop tells every weight to move a little higher or lower to reduce error. After many tries, accuracy improves, just like hitting the bullseye more often. We pulled back the curtain on a key area of AI. Modern AI learns from data, not rigid rules. Neural networks, input, hidden, output, are brain-inspired models at the heart of this shift. Deep learning means many hidden layers, learning hierarchical patterns to solve hard problems. Training plus backprop makes models accurate,